In our last notes and activities, we were talking about Lewis dot structures, and we were making Lewis dot structures for different atoms and molecules and putting them together. In these notes, we're going to take a look at what's called the Vsepr model, or the valence shell electron pair repulsion, to see how the Lewis dot structures affect what shape molecules are in. The first question of these notes is, what types of electron pairs are in a molecule? Now this refers to the electron dots that we have in the Lewis dot structures for molecules. So we're going to take a look and see what kinds of electron dots we have around atoms in a molecule. Atoms in a covalent molecule can have two types of electron pairs if we look at their Lewis dot structures. So for example, over here we have NH3, okay, ammonia. Here's the Lewis dot structure for NH3. So we can see that there are two types of electron pairs here. We have bonded pairs, like these guys right here. Okay, these bonded pair electrons are involved in bonding two atoms together, the nitrogens with the hydrogens. And then we also have lone pairs. Okay, lone pairs are these guys here that are nitrogen's own valence electrons that are already paired up with each other that are not involved in bonding. Okay, so the lone pair is not involved in bonding. The bonded pair is involved in bonding. Now, the reason why we make this distinction is that because both of these types of electron pairs are going to affect the shape a molecule makes, and that's what the Vsepr model is all about. It's all about figuring out what shape these molecules are. Alright, so the trick with these is that both types of electron pairs, both bonded and lone pairs, want to be as far apart from each other as possible because electrons are negatively charged and so they will repel each other. So that's where this Vsepr model comes into play, where it's valence shell electron pair repulsion. Okay, so they want to be as far apart from each other as possible. So this is going to set up the different shapes that we have. So let's take a look at three different examples of molecules and analyze their number of bonded versus lone pairs. Alright, if we take a look at the first of this example, CH4, we see that carbon is bonded on all sides. So in this case, we have all pairs are bonded pairs in this molecule because we have no electron pairs of its own for carbon that are just kind of sitting there alone. That's unlike the second example here with NH3. So we can see that we have at least one lone pair and all the rest of them are bonded to H. So in this example, we have one lone pair and three bonded pairs. Alright, now in our final example of H2O, we can see that oxygen here has two lone pairs and two bonded pairs, bonded to two hydrogens. So let's write that down. So in that one we have two bonded pairs and two lone pairs. Alright, so we're going to take a look at electron domains and also how these bonded and lone pairs are going to contribute to the shape of a molecule. Alright, the next question we're going to tackle is, what are electron domains? So another just kind of vocabulary word when we're talking and working with Lewis dot structures. Alright, so an electron domain is basically the area around an atom that is occupied by a pair of electrons, whether it's bonded electrons or lone pair electrons. So when we're looking at a Lewis dot structure, it's basically in the Lewis dot structure, how many sides of it have electrons on it. So let's take a look at a few examples. Alright, let's take a look at the example NH3 again. Alright, so if we do the Lewis dot structure for NH3, we're going to have nitrogen with 5 dots, right? And he's going to be bonded with 3 hydrogens, okay, each having their own dot to contribute to share. Alright, and now we see that because in this Lewis dot structure that nitrogen has electron pairs on all 4 sides, we can say that NH3 has 4 electron domains around nitrogen. Alright, if we take a look at a second example, CO2. Let's take a look and see how that's going to work. So we have carbon in the middle with 4 dots, okay, and we've got 2 oxygens going to be bonded to it with its 6 dots. 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6. Alright, right off the bat we can see that we've got some lonely electrons, some unpaired electrons that we can't have. Okay, can't have those in a Lewis dot structure. So if we have unpaired electrons, we have to put them, in the middle to make double bonds. So let's see how this is going to work. Alright, so that's our final Lewis dot structure when we've put our double bonds on either side. So here we can see that carbon doesn't have 4 electron domains like nitrogen did above it. Carbon only has 2 sides with electrons on it. So that means we've got 2 electron domains around carbon. And if we take a look at oxygen, oxygen has 1, 2, 3. All of the oxygens, both of the oxygens have 3 electron pairs, or 3 sides that have electrons on it for oxygens. Alright, so the carbon has 2 electron domains and oxygen has 3 electron domains. Alright, so again, electron domains just how many sides of an atom has electrons around it when you're looking at the Lewis dot structure. Okay. Alright, now these electron domains are going to help us figure out the shape of molecules. So let's go on to our last question of these notes. How does Vsepr contribute to the shape of a molecule? Alright, so now we've come to kind of the point of this lesson here is molecular shape and how we get different shapes of molecules because of the repulsion in the valence shell. Alright, so how does Vsepr, or valence shell electron pair repulsion, contribute to the shape of a molecule? Alright, the key concept for this is that all those electron pairs, whether they're bonded pairs or lone pairs in our Lewis dot structures, take up space around the atom. And so they're going to have an effect on the shape of the molecule. In fact, lone pairs take up a bit more space than bonded pairs, and so they're going to push down those bonded pairs a bit more and affect that shape. So let's take a look in detail about how we can relate structure and electron domains and bonded pairs and lone pairs, all with the shape of molecules. Alright, so for this discussion we're going to set up our paper to look like this. So we're going to have a molecule, we're going to put down its structure and like structural formula. We're going to talk about the number of electron domains around the central atom, and then we're going to talk about the number of bonded pairs versus lone pairs and what shape that is, as well as the bond angle. Alright, so our first molecule is methane, or CH4, and if we draw it out, okay, we're going to have C with bonds to 4 different hydrogen atoms, okay, just like this. And so we can see that all of the electrons around carbon are bonded pairs, so we'll have 4 bonded pairs. In fact, all sides of carbon have electrons on it, so that means that the number of electron domains is also 4. And there are no lone pairs around carbon because he doesn't have any lone pair electrons, so it's 0. And so this shape here, where there's 4 domains, 4 bonded pairs, and 0 lone pairs, is what we call tetrahedral. And the bond angle is 109.5 degrees. Okay, which this is what it means. It means the bond angle between all of the hydrogens are 109.5 degrees. Okay, so they're all 109.5 degrees away from each other. If you were to actually take a compass and figure out the angles between all of the atoms. It's 109.5 degrees all the way around. Alright, our second molecule is ammonia, or NH3, and so if we draw out its structure, okay, we're going to have nitrogen attached to 3 hydrogens according to our honk rule. Nitrogen must have 3 bonds, and he also has a lone pair up there. Alright, so if we take a look, again, nitrogen is going to have all 4 sides have electrons on it. However, this time he only has 3 bonded pairs because he's only making 3 bonds. And he's got 1 lone pair up here on top. So that's his lone pair. Now, in this case, where we have 3 bonded pairs and 1 lone pair, it's what we call a pyramidal shape. And you'll see how this looks like, basically a pyramid if you hold this kind of molecule in your hand tomorrow in the lab. So the bond angle for a pyramidal shaped molecule is slightly less than that of tetrahedral. It's 107.3 degrees. So again, what that means is that the bond angles between all of the hydrogens are 107.3 degrees. Okay. Now it's slightly less because of what I said in the last slide, that this lone pair is going to take up a little bit more space than all the bonded pairs. So the lone pair is going to push down these bonded pairs a little closer to each other than the tetrahedral shape. Alright, our next example is the molecule H2O. So if we draw out the structure of H2O, we're going to have an oxygen, okay, bonded to 2 hydrogens. And remember, this oxygen also has 2 lone pairs around it, okay, that are not involved in bonding. So again here, around oxygen, the central atom, we have 4 electron domains because all 4 sides have electrons on it. 2 of them are bonded, okay, and 2 of them are lone pairs. And so this shape here that has 2 bonded pairs and 2 lone pairs is called a bent shape. Alright, and so the bond angle for a bent shape is 104.5. Let's see, 104.5 degrees. So again, what that means is that the angle between these 2 hydrogens, not around the backside where the lone pairs are, but on this side over here is 104.5 degrees. And again, it's because these lone pairs are pushing, they take up more space, so they push those hydrogens closer together to an angle of 104.5 degrees. Alright, we've got 3 more molecules to take a look at, and our next one is CO2. Okay, and so if we draw out the structure for CO2, again, we're going to have a double bond here. So carbon double bonded to oxygens. Each oxygen has lone pairs. Okay, just like this. And so we see now here that carbon in the center atom doesn't have 4 electron domains anymore. He only has 2 sides of him that have electrons on it. So he only has 2 electron domains. Okay, so he has 2 electron domains. All 4 of his electrons are involved in a bonded pair, and he's got 0 lone pairs. Alright, so it's kind of similar to the first scenario that we saw, except now instead of 4 electron domains, we only have 2 electron domains. And this shape is called linear. Alright, it's called linear because basically the atoms in this molecule are lined up in a line. Okay, and the bond angle is 180 degrees, just like a line's angle is 180 degrees. So we've got 180 degrees between each of those atoms that are bonded to the central carbon. Alright, so this is a linear shape. Alright, our next molecule is going to be CH2O. Okay, and when we draw this one out, okay, we're going to have a carbon in the middle, and he's actually going to be double bonded to this oxygen, and he's going to have 2 hydrogens hanging off of him as well to complete his honk rule of having 4 bonds on carbon, 2 on the oxygen, and 1 for each of the hydrogens. Alright, so if we take a look here, carbon has 3 sides, okay, that have electrons on it. We've got 1 side with a double bond and 2 sides with a single bond, so 3 electron domains. Again, all 4 of carbon's electrons are involved in a bond, so all 4 are bonded pairs, and we have 0 lone pairs. And so when we have 3 electron domains and all of them are bonded, none of them are lone, it's what we call a triagonal planar shape. And it's kind of called a triagonal planar because it's a very flat molecule. It's one of the only ones that actually sits very flat on your hand. And it looks like a big triangle. Okay? And so this bond angle between all of them, because it is a triangle, it's going to be 120 degrees. So this is like an equilateral triangle where all of the bond angles are 120 degrees away from each other. So that means all of the atoms that are bonded to that central carbon have 120 degrees separating each other. The last molecule that we're going to take a look at is a little bit more complicated because it doesn't have just one central atom. Alright, so this molecule is CH3OH. And in this molecule, we have carbon attached, and making 4 bonds attached to an oxygen, which is attached to a hydrogen. Okay. And then carbon here is attached to hydrogens on all sides as well. Alright, so we see here that we don't have just one central carbon. We actually have one central atom. We actually have 2 central atoms. We have a carbon here that is attached to hydrogens, and we also have an oxygen here that has more than one attachment to it. So we've got 2 central atoms. Now, each of the atoms, you have to look at each of the atoms separately. So for carbon, carbon's got 4 electron domains because all 4 sides of carbon have electrons on it. All 4 of his are bonded pairs, and he has 0 lone pairs. So around carbon, the shape is our tetrahedral shape. So we have a tetrahedral shape around carbon, and so that means that all of these guys here, all of these hydrogens around carbon, like everything that's linked to carbon, is separated by an angle of 109.5 degrees, okay, around carbon. Now if we take a look at oxygen as our other central atom, okay, again, he's got 4 electron domains because he's got 2 lone pairs and 2 bonded pairs. Okay, so he's got 2 bonded and 2 lone pairs. So what that means is that around oxygen we have a bent shape. So we can say bent around oxygen. Alright, and so again, the angle around a bent shape is 104.5 degrees. So that means that the angle between the carbon and this hydrogen here is 104, okay, 0.5 degrees. Alright, so when we have more than one central atom, you have to determine the shape around each of the center atoms independently. Alright, so that's the end of these notes. Tomorrow we're going to do a lab, a dot and Vsepr lab, so you guys can get kind of the hang of figuring out what type of shape molecules, covalent molecules, can have when they make their different bonds. Alright, so we'll see you tomorrow.